Yeah, I've shared my screen. Uh,
Ye-
and
Yes,
just for so see, say this is a neural network, okay, and this is the last layer. So what we call this as ALM.
sorry, your voice is a little incomplete in some places.
Uh, oh, hello. So is this one better?
Yeah, yeah. I think for now it's better.
Okay, so I'll use this. So this other device, I'll
Okay,
use this for a voice. Yeah, I'll write
okay, sir.
here.
Okay, sir.
Okay. Now, okay. So yeah, this is the last layer, right? So HL and HL is what we call Y hat also.
Yeah. So
Whatever.
I was asking for HL minus one. For Y cap, I understood that part. I understand. So when we go
Here,
H,
right?
yes,
Here.
sir.
Let's
Yes, sir.
say so this is H2 and A2, A1
Yes,
and H1. Okay. So you are
yes.
asking for if I do let's say loss function with respect to H2.
One element of H2 when we go, or even H2 as well.
Yeah. So that's all. Like any element of this,
Yeah,
right?
yeah.
So if you wanted to do that, so here loss is there.
Yes,
Let's
sir.
say loss is minus ln of y hat, right? So that's what
Yes, sir.
loss is. Now you want to figure out this, so you have to do the back prop, right? So you will go, since y hat is the only one related to L, you have to do that. Then y hat is related to AL, right? So
Yes, sir.
I'm calling AL. So HL is y hat, right?
Yeah,
So
yes, sir. Yes, sir.
AL, then so AL has two things. It has W. Uh, this one I'll call. So whatever here weights are W1,
Yeah,
and
yeah, yes.
here they are W2. And this AL is like W2 and H2 plus B2, something
Yeah,
like that, right?
yeah.
Now, either you can do with respect to W2, or you can do with respect to H2, right?
Yeah,
Something like that. But here we'll require H2. Will not require this one. Like there are two paths, but
yeah.
this path we won't take as of now.
Yes, sir.
We'll do it when we require this, right? So okay. So here we'll do AL with respect to H2,
Yes, sir.
right? So this is what we have to do. Now now your question is why there is summation happening, right?
Yes, sir.
Okay, so uh, okay, so how AL looks like is it's going to be a vector. Okay, let's say AL1,
Yes,
AL2, AL3, right? And
yes, sir.
it would have formed using some W. Like here it will be so here this will be like W211, W22, two layer two neuron 1 second.
Yes, sir. While doing this, I noticed in the deep learning book, I think the Ian Goodfellow book, they used layer notation as superscript. I found that slightly better to look at for matrices at
Uh,
least.
Yes, yes, but so whatever we have used here, we can go with it. Like,
Yeah, it is
uh,
the same thing.
okay, so I'll explain. So this is layer two,
Yes,
then
sir.
neuron number, so neuron two and first weight of that.
Yes,
Okay,
sir.
layer two, neuron two, and second weight of that.
Yes, sir.
Layer two, neuron two, and third weight of that. Okay,
Yes, sir.
third weight of that, and we'll have two inputs like H1 and H2, right?
Yes, sir.
Uh, so I should write it as H21, H22. Okay, this is what it is. Now,
Yes,
if you do let's say AL1 or AL, so this is AL. Now you want to do AL with respect to dow H2, right?
yes, sir.
So what you have to do is this is a vector. This is also a vector.
Yes, sir.
right? So you'll get a matrix.
Yeah, sir, Jacobian. Yeah.
Yeah, kind. So if you do, let's say now AL one with respect to Dow H21 and AL1 with respect to Dow H22 also, and similarly you do for all six,
Yes, sir.
right? So okay. Now what happens is if you do this one H21, where does it contribute is uh, I think there is some mistake with the metrics. It shouldn't be H. Ah, okay. I wrote with respect to AL, not uh, it's AL should be. um, Give me a minute. With two. mm, uh, some this matrix. So AL should be of uh, if I have three here, two here, then oh, okay. Sorry, I think I no,
Okay.
that should be other way around, right? Three.
If we write
So
it down in summation form, it should be easy to differentiate, I think.
yes. But here this equation is incorrect. Like the
Oh,
weights,
okay, okay.
this matrix multiplication what happened, right? A equal to wx. That's how we have used here.
Yeah, yeah.
So the first has this. So that's where I'm correct. That should be 211 W2 2 3. I'm missing something. Ah, okay. I, so the mistake was that it should be related to this one, right? Not here. Like that means this two are coming here. That's what I should have written. Like
Oh,
WL1, WL2, right? Something like that. Then WL. So this first neuron L11, L12, WL21, WL22, T1, and WL32, right? So
yeah,
I wrote other way around. Okay.
yeah.
Now it is okay. So now this is H11 and H12. Sorry, this 21 and yeah, something like this, right? Now if we have AL with respect to Dow H21. So this H21 has contributed where? Like once it has contributed here, right? If you
Yeah.
see, so, and multiplication similarly here also it would have contributed. here also it would have contributed, right? H21.
Right.
So if you do back prop, you have to do across this all three paths, and if you do that, you have to sum it up. So
Okay.
something like a, let's say L1 with respect to uh, H21 plus AL2. So that is another one, like the second, whatever you get in a vector, right? Second one. With respect to that also you have to do, and plus now AL3 and H21, right? So these three paths are going on, and so across these all three paths you have to sum. So this summation should happen that way.
I suppose I missed that. Okay. I went AL1 and H21 and then just okay.
Yeah. So here it is contributing three places. So that's why we have to sum it all three things.
Okay, it makes sense now.
Okay. Uh,
Oh.
that is okay, right? Other thing you'll be able to understand.
Yeah. Others I was able to understand very much.
Okay, fine.
Okay. Thank you, sir.
Uh, okay. Any other questions? Anyone have? Okay. Anything you want to cover? I think so. We had an extra session on this, but that is okay. You can ask now if you have any question. Um, if anything you wanted to get clarified, I'll explain.
Sir, in that derivative you use, right? Why you stop till three parameters L1, L2, L3? Is just an example you took, sir.
Yes. So here we use three neurons. That's why three. It should
Oh,
be k neurons. Okay. So
okay.
last has k neurons. Yeah.
So then matrix but multiplication under one change, right? Same result we'll get.
Yes. Same result. Nothing will change. Just you have to adjust, right? So whatever size is, you will get that size of
Okay.
output and
Okay. Thank you, sir.
okay. Uh, anything else?
Sir, I have one doubt.
Yeah.
It is not exactly relevant, but I wanted to ask, say, for example, in the output layer, we are trying to estimate probabilities, and we used that e to the power xi divided by e to the power sigma xi formula.
Yes. So softmax we
Of
use.
x. Yes, sir.
So that is e power. Let's say we have three. P, Q, and R are the let's say AL. So you'll get e power P and e power P plus e power Q plus e power R. So this is what a summation is, and similarly you'll have for e power Q and this whole summation. I'm calling this a
Sir,
summation, and so like that. Yes.
sir, say for example, we substitute e with 2. Will this softmax work?
E with two.
Yes,
You
if we
wanted
substitute
to use
base
uh,
base 2 instead of e.
will this work or not?
And why have we used only e? That was
Yes,
my
it will work. So then you have to use ln or log 2 base something, right? So when you will calculate loss or something, you have to use log 2 base, then it will work. Uh,
okay.
So like for classification problem we use cross entropy, so we have to take base 2 instead of E.
no. This this question is out of that. So cross entropy will remain however we do. Yes, but I mean, if you do this way, like you don't use e at all, you use some other number. E is also a
Yes, sir.
constant, so if you use any other constant, then that's what you have to use, the log base of that constant for loss calculation.
Okay.
Okay. So will not, by default will not change, but if you wanted to do it, that is the question.
So I know it would make the calculation very tough after, means like while we are making the differential equations and doing that whole procedure, it will make it very tough. But this is one scenario. If someone decides that E is, then how will it change the whole thing? Will it
So
change the
yeah, it will
variables?
affect. So let's say you a power x, right? So do you know what is differentiation of this?
A
Yes, sir.
power x
We'll
log.
just multiply it again by e to the
Log
power.
of
So
yeah.
yes, sir. E to the power a will have to means
Uh,
like log base a e will have to multiply
E to the power x log a.
uh,
e to the
yeah, something like that, right? So this extra thing will come up, whatever, like
yes, sir.
some extra thing will be there. But if it is e power x, the differentiation is e power x. So this is easier in differentiation. This
Also, sir, it will
extra,
not be e to the power x log a. It will be a to the power x log.
yeah, a to the power log. Okay.
Yes.
Yes, that is. So something. So this extra thing is coming up, but here it is like log e base e. That's why. Sorry, log e, and of course it's e. So that
Yes,
that
sir.
that makes it one. We don't have to do this. That's why we use e base and not any other constant.
Sir, I have a small question. I filled the form.
Yeah.
Can you see the form once? It's a tiny
Um,
question only.
so um, your question is related to the book, is it, or the other one? What are the steps to solve week 3 backward program practice assignment for question 8? That one, or
Sir, the book one. Sir, I didn't understood what is the meaning of weight space symmetry.
mm, okay, this is very difficult. Uh, Actually, I myself have never haven't used that book for the reference. That's why, but I'll try. Book last time somehow I accessed it.
Sir, I have one. I want to give one suggestion also, sir. Like in degree level, the classes are not as similar to the diploma level, so they want us to study by our own. So we don't know how to study in a way that we are not misdirected. Like there are lots of books and they says a lots of things and then it mix up and
So I would suggest that go through the lectures, which explains most of the thing, which is relevant to the course, right? Like other things you can do. So see other things. That's what, like in DL there are so many books and everybody uses self-created like notations and all. It makes difficult to understand. But I would suggest that go through the like follow the course one, because you'll see that exam will have that notations which are used in course, uh, right? So you won't miss it, like something like that.
yes, sir.
Mm, uh, Uh, so I've shared my screen. If you can see, so we are in page 284. Here it's the
Sir,
question.
I wrote about the second textbook, this the I in Goodfellow one. In that it is given.
Okay, that I
So they were on the portal. There were three textbooks. This was the first one. Then the second one I mentioned about it.
okay, okay. I, uh, so is it publicly accessible? I think this one, right?
Sir,
Chapter
I
8.
think
Here, what is the space? 271. This one, right?
sir, the screen is showing the previous book only.
Ah, okay, okay. Okay, this one.
Yes, sir. This book.
So,
So
uh,
it was written in bold color, the weight space symmetry, and like bold it was written. Uh,
okay.
maybe I have mentioned the wrong page number then.
Um,
So it was so when you scroll down there was a saddle point. It was written at the bottom. Yeah, similar in this fashion. It was written in the bold one. These two words.
but
I think I wrote the wrong page number.
I don't see it here. So,
Sir, do one thing, sir. Control F, sir. Search the word actually in the book.
yes, I did search
Yes,
it.
sir. Weight space limit to this one. Yes, sir. This
Yes.
paragraph and model identifiability.
Uh, mm, uh, I have no idea about this actually. I uh,
Yeah.
never
Yes, sir.
never had this. Um I think this is something related to if I can say it is this is related to really math background, and I don't see we require this much, but that's good. You will be able to understand it. I myself I don't understand this much. Uh, so I don't know what does this mean, like how they mention this. Uh,
Yes, sir. Lots of new jargons are there, and every time
yeah, it
it
will
tells
be there.
something.
So you can, yeah, it will be there. So I think you have to. I'll ask Karthik if he is able to, but I don't think so. He will be able to. Uh,
Oh, okay, it's okay, sir.
uh, some somebody has what are the steps to solve week 3 back propagation assignment 1 question 8. uh, Uh, Forward propagation, why don't we integrate? Uh, okay. Else, so okay. So here we have tried to give you the answers, like what you have to do to solve this. So somebody has a doubt in question 8 of this, written in that Google form. So now you are taking derivation with respect to W3, right? That's what the question says, and you have to do this two derivation to figure this out, right? So one is loss with respect to the A3, and then A3 with respect to W3. So this last part, which is loss with respect to A3, if you want to do that, will that will come out as but you will see it will come out as uh, y hat minus y, right? So that's what you will get doing this. If I show you um,
So like these questions we can do in collab, but in exam, how we will do such complex calculations?
uh, I don't think okay, uh, so give me, I'll do this. Okay, I'll I'll show
No,
you
so
how.
like weight matrix multiplication with the vector, and weights are also in decimals, that kind of thing.
Okay. Okay, see, we have this question. So I'm currently taking this one only, which is practice assignment 8. So this solution was given to you, right? I'll show you. So we have few weights. For example, 100 111 011. So and W2 is 111 111 001, and there is W3, which is 100 111. Okay. Now x is given to you, and y, true y is also given to you. So x is 101. Okay. Now you have to do, you have to find first a layer one, uh, something like this. So if you see the structure of it, it's like three inputs are there. So this x, you can see there are three inputs. Then there will be three neurons. That's why we have 3 cross 3 matrix, and we'll have another three neuron. So again we have uh, 3 cross 3 matrix, and then another set of neurons. So this is A1, H1, A2, H2, A3, and I can call H3 or y hat. Whatever I get is y hat, and that y hat I'll use for a loss calculation. Okay. So this is my this is my architecture. Now I have to figure out what is A1. So A is going to be Wx plus B. So as of now, B is told that ignore it. So we'll ignore that. Okay, but otherwise it should be there. Now this weight is which is 100 111 011, and x is 101. So this is a like simpler matrix multiplication. I would say this is a difficult one. You can do this. So we have 1 for this, right? Or if I write it here, you will get a vector of 1. Then you have to sum all 3, so that is 2. Then you have to sum last 2, which is 1. Okay, so this is what you will get. Then h1 is going to be, you have to send this through the sigmoid function, which is 1 by 1 plus e power minus 1, then power minus 2, then 1 by 1 plus e power minus 1. Okay. So here also it looks like kind of easier. Like if you can able to do e power minus 1, so you'll have calculator right there, where you can calculate using like exponential, like what is e and all. So calculator you have to use for the exam, right?
So can't the values of these be directly given in the question, because using calculator is very difficult. That calculator is.
Uh,
So the way in statistics too, we were given the formulas in the question itself. So the same way, can't it be possible?
no, we like that much you have to do. So this is something, it's not that difficult, right? You have to figure out one and then another. Like it's not, I don't see much issues here, right? You can do it. So if we give it, I don't see a point of this question at all. Like I don't know. Okay, but this is a relatively easier calculation. You can do it using calculator. I This much pain you have to take. Okay, then same thing you'll do with a2. We'll figure out a2. So for a2, this will be the x, right? So a2 will be like w2h1. Okay, and similarly you will do h2, a3, and h3, right? So this all you'll do. H3 will have final output, y hat. You can call this as y hat. Now you'll compare this with the loss function. So loss is going to be, so since you know that this is a sparse vector, like there is only one place it can be, like, so y hat is going to be ln y some class which is true, right? So wherever the true class is, that's what will be remain. Like I think it should be l or whatever the notation is, but this where the true class was given, right? So here if you see, we have okay, y, I haven't, right, but it is y is 0, 0, 1. Okay, so this y3, you have to take a y hat of 3. That's what the log you have to use here. Okay, that is the loss. Now the eighth question which I wanted to do is, so which is, how can I find with respect to w3 at this weights I want to do. So L is connected to y hat, y hat is connected to a L, uh, and AL is connected to W3, right? So you see the architecture, this here, then A3, and this weights will be the one it is related to. So that's why I have to do this, and this calculation is little easier. Like you, if you do this, this is a simplified form of like y hat minus y. It will boils down to this. You can try it. So slides are given. So this is a easier one. You will get 1 by y hat, something like that. You will get derivation of that. Here you will get a little bit of a matrix kind of thing, and after you do the multiplication, you will get this vector. So this is form of vector. Okay, this is a column vector. How it will look like. Now AL with respect to W3 you have to do, and if you see, that is uh, that is going to be W311H2. Okay, how it's going to be, like, for example, this is here it is AL1, right? So we'll have H21, H22, H23, right? So this 3 will go, and you'll get a summation of that. Okay, so it will be like H21, H22, H23, and this should be W 311, W3 12, W3 13, something like that, and summation of that. So you'll get this matrix. Now you have to do this derivation. So if you see with respect to W3, you have to do right. So okay. See, if there is a vector and this is a matrix, let's say W something, okay, 1, 2, 3, 4, and you do a derivation of that with respect to there is a vector, let's say size 2, okay, A1, A2, something. So this what you want to do. How will you do it? You will first do this. You'll take this and you'll do derivation of this 4. Okay, and again you will do you'll take A2 and you'll do a derivation with respect to that. So you will get a tensor. You'll get a like something like this. Okay, you'll get a tensor. This is called tensor. Like two uh, matrices are then one after other or something like that. But you will realize that since nothing this weights won't contribute to the second one, right? Sorry, this won't contribute to the first one. So it will become 0 for this. So here you will see getting 0, and here you will also get 0. I can show you with another example, or maybe this one also. So I'll write what how A3 looks like. So see, A3 looks like this: 1 0 0, 1 0 0, 1 1 1, and then here I got 0 0.91, 0 0.91, 0 0.67. Okay. So here this is the output. If you see, is very easy. You just have to sum it up like 1. So this there again 1, and all 3 you have to sum, right? So it's a relatively easier calculation. Now if you want to do A3 with respect to W3, first you'll do differentiation of this whole with the first element itself, like A31 with respect to W3 1 1, then 3 1 2. But see, this is a like I'm explaining it a little bit more, but ultimately you'll get a W transpose as the output. Okay, so to make it easier, the calculation we have made this. Like for example, I said that here you will get 0, and here you will get 0. Now you can create a tensor which will take more space, and also to not give more space and make computation easy, we have used this as a like we are going to make it as a matrix, like, which will have this values and this values. Okay, that's what we have to do. Now same thing you'll do with the 1 3, right? So same thing you have to do again for the this weights and all. And if you see for example A31, which is this, right? So this weights were included, which are here: 3 1 1, 3 1 2, 3 1 3. These 3 were involved in computation of A, right? First element of A, these 3 were involved, but not rest of them. So here something you will get. But what about this? Was this any contribution did it give for a computation of the first element of A? No, nothing, right? So after that, no contribution. So you can say this will end up giving 0 as a differentiation. Okay, so you'll get 0 in the differentiation. Something you'll get here, and that something is H, like this H21, H22, H23. This is from the previous layer. Okay. So this 3 you'll get. Similarly, you'll H22, H23. Similarly, you will do for the second one, and you'll see that the first layer will become 0, and here you will get again H21, H22, H23. Okay, something like this. So this is what uh, this again if I do that. Yes, that's right. So this is what you'll get. Like again and again, you'll get that. Now you wanted to do this multiplication, right? With in backprop, you want to do this multiplication. So how will you do that? That is the question. I can so let me use slides for this. That has uh, so the thing we are looking for is no, we are looking for with respect to the weights, not hidden units, with respect to the weights, right? So that's what this whole calculation is. You'll get this, right? So you can see we are getting this one. Similarly, that's what we get when I wrote it a little bit like that. So if you wanted to do this multiplication, now we are making it a little bit of simplified version of this, and you will come across that the simplified version of that is the transpose of like H2, right? So that's what we used here. For example, H2 transpose. If you do that, and here we already figured out y hat minus y. So this is a vector, and this will be a so this is a vector, a column vector, and this will become a row vector. If you do this multiplication, you will end up having this matrix. Okay, so this is what we did. So, like you can see, we were also able to come across this answer only in a different way. Okay, yeah, I can show you maybe, but that's what. So this is a vector, and this is a column vector, and this is a row vector. If you do the multiplication, you'll get a complete matrix after that. But in reality, like in we have a tensor, but to reduce the
Are we
computation,
are we doing outer product here, or like transpose is
outer product.
so to get the matrix?
Yes, right. So if you have a column and a row vector, you do the matrix multiplication, you'll get a tensor, right? Sorry, you'll get a matrix. Like let's say 1 2, and this is 2 3. You do multiplication matrix. So 1 with 2, like this, so you'll get 2. Then 1 with 3, then 2 with 2 is 4, and 2 with 3 is 6. So this is what you'll get, right?
Yes.
Okay.
Sir,
Yes.
actually, I did a similar problem like this. When I was doing the problem, they used the formula like delta of nabla of W3 is equals to del L by del Y predicted into H2 and transpose of that.
Yes.
So can you please tell how we are getting H2 transpose into del L del Y? That will actually help us really solve this.
That's what it is, right? See, we got this answer. We got this, right? So forget about transpose before that.
Yeah.
Can you understand this part?
Uh,
Why, how this came up? Now, how will you
yes, sir.
write this in this way? That's what leads to H transpose. So you wanted to multiply this all the,
Yes, yes,
you
sir.
can see this
The
is
the part that you have encircled in the right hand side.
yeah,
How can we show that that is del L by del Y predicted? Was that if that can be established, I can understand what is going.
del L by del Y predicted.
Y predicted, yes.
Uh, no, it can't be Y predicted because we want to do with respect to weights, right? So weights, see, in last, yeah, so in last layer, this is A, to which the W's are associated, like A3 is W3H2. Y hat has no direct connection with W, like weights, right? So Y hat has connection with A3, correct? Like some
Yeah, yeah, yeah,
like
yeah,
soft max of A3, like something like
yeah,
that, right? So it has
yeah,
connection with this, but it doesn't have any connection with weights. So if you wanted to reach the weights in backprop, you first have to do with A3, then you can go to weights. So Y hat here, Y hat won't work. Like it can't be Y hat. It has to be weights. Uh, Sorry, it like something like so. Not this. This is what we want to figure it out. But here it can't be Y hat. It has to be A. It has to be
okay, okay.
A. So yeah. So that way you can do that one. Now few others you will come across. So I'll give you a easier solution to this. That is how will you do it? Okay. So for example, we had this architecture, okay, and where we had three kind of weights and three layers and all, right? Now what we actually wanted to do is, so the whole idea of backprop is that we wanted to update the weights, right? Update the weights and bias also. That is the task for which I wanted to do backprop. So you'll see that we'll do with respect to uh, first weights. Then if bias was there, then I would have done with that also. And then similarly, I'll do with W2, B2 also, W3, and B3 also. So this six kind of uh, back propagation I have to do, right? But you'll see that if you are able to do with weights, and then bias is relatively easier. You just have to use one instead of the um, H2 transpose. Okay, that will work. Now, okay. So with respect to W3, you are able to figure out that it is with respect to A3 I will do, and then A3 has a connection with W3, so I'll be able to do it. Okay. Now let's say you want with respect to W2, so what you will do? You'll do till A3 you'll do, right? So let's say this is A3, sorry A2, and now this the weights which are coming here has like are W2s, right? So that's what I wanted to reach there. How will I reach there? So this is Y hat. This is A3. I already reached here. Like by writing this much, I reached here. Now, if I take weights, then it won't work. What I have to take is I have to go and take this H2, right? H2 has the only path to the weights 2, right? H2 is the only one path exists which can leads you to weights 2. So that's why I have to do A3 with respect to H2, not W2. I can't do it. So for example, you can even think like that. Let's say um, you have W, you have H, something like, let's say W3H2, and this 2 produces A3, right? So either you can go this way and chain ends, right? Nothing is after that, like it ends there. But if you go there, you can go to A2, then A2 can leads to W2, right? And then chain ends. Again, A2 has this power that it can leads you to H1 and something, right? So you can see in that way that this is a chain, and which chain you want to follow, that you have to decide in that way. Okay, so in our case, uh, which is here, we wanted to go H2, then H2 knows what happened in A2. That A2 is the only one connected to W2. Okay, so dow A2 by dow W2. That's how I can reach to W2. Similarly, I wanted to reach W1s also, which are, this won't change. A3 with H2 won't change. H2 with respect to A2 also won't change. But now I can't go this way. This is end of path. There is nothing after that. But A2, if I take it with H1, which is from prior layer output, then H1 are connected to A1, and A1 are the one which are connected to W1, right? So this chain elongates. So this is the only thing you have to figure it out to do the back propagation, right? So this part is which is everywhere, uh, will always, if you use cross entropy, okay, if you use cross entropy loss, then it will always comes out as y hat minus y, okay, del L by A3, del A3. Okay. Now, so here it changes. Then something is here, and that continues here also. So this part I have to. So here one change is there. Here another comes up, and then after some changes are here also, right? So something like that. Now you wanted to with weights. So as just now we looked at it, that if it is weights, then you have to do H2 transpose, right? So you can think like that. Let's say I have W, uh, H, and B, right? Something like this. This is a, let's say I'll call it as Z something.
So I have a question here.
Yeah.
Like, so these biases, to which neuron it is attached to? Because if we calculate the parameters, number of parameters, then I'm stuck between like how to count the bias.
So all the neurons have one bias. All of them.
Okay. Okay, sir.
So one means not value one, but one bias. Like,
So if there are n neurons, then there will be n biases.
yes.
Okay, sir.
Yeah, so let's say I have this equation. Just think this is a simple equation, not matrix, vector, anything, just some scalar value. Okay, now if I ask you to do it with respect to H, you'll figure out that this is going to be a W as answer. If I tell you to do with respect to W, you'll say that the output is going to be H. And if I ask you to do with respect to B, then the one is the answer, right? So similarly, you can think here that if I have to do with respect to weights, then the answer can't be W. It has to be H only, right? So there are three things which can come out as answer, either W, H, or B. And if I'm doing with respect to W, then H will come out. If I do it with H, W will comes out. Okay. In some weird format, uh, transpose, whatever you can say, but it will come out like that. Okay, so here it is like a row vector and transpose of that. If you do this, you have to do outer product, and you will get a matrix, and that's what the answer is. Okay, so one check you can do is, let's say your weight matrix was 3 cross 3, and back propagation you did, and it didn't come out as 3 cross 3. That means you have made some mistake. It can't be that. So it has to be of this size only. Okay, so derivation will be of that size, right? Now I'll show you with what you can do with respect to W2. Okay, so dou L by dou W2, what you have to do. So so it's like this. So this four are there. This part is clear that this is always going to y hat minus y if it is cross entropy. Now A3 with respect to H2. Any guesses what is going to be answer? Somehow it is going to be
W.
W, which one? 2, 3,
Uh,
1, which W?
3.
Last
W3 it should be.
W3, right? So this is going to be W3. Now here also one catch is there, that the catch is that you want to do yeah, maybe I'll use the slides to show it. So this is with respect to the hidden layer. Okay, backprop with respect to hidden layer. I'll just go there. Back propagation respect to this output I am doing with respect to hidden unit. Okay, so if I do with respect to hidden layer, you can go through this and and uh, unit. Yeah, so this is, we can now with respect to hidden unit like hi something, so you can see they are doing I plus 1. So for example, what we are doing is we are doing with respect to h2, right? We have h2 here, I is 2. So you can see this w3 transpose you have to take, and whatever prior to that. Okay, so this you can come here and understand this how this comes up. But to make it simpler, I'll just say that what you have to do is you can't write here w3, but you have to bring it in forward and transpose of it. If you do this matrix multiplication, that's what this will be. Okay, if you wanted to understand this, you can refer this. Here it is, why it should be in front and not back, why it comes out like this. Okay, I can do that, but it will take some time. Okay, uh, but that is the idea, that you have to do that, and you can see this is I plus 1. Okay, so we are doing with respect to h2, so it should be w3, and you have to take transpose, bring in front. This is how you can remember, like how will I do it, is this is how you can remember, and you can do it. Now h2 with respect to a2. So h, what was h? H was sigmoid of a, right? And sigmoid you can take like this, like so the derivation of sigmoid is so the derivation of this is going to be h2 into 1 minus h2. Okay, that you can write here, h2 1 minus h2, and this is going to be a column vector. This is also going to be a column vector. You just have to subtract one from all of them. Okay, so this is a column vector. This is a matrix. Okay, this matrix and all rest of them are column vector as of now. Now a2 with respect to w, any what will be the output? Here it is w2.
X.
X, no,
H.
h, which one?
H1.
H1, right?
H1 transpose.
And transpose of that. So
Yes,
this is
yes.
going to be a row. So this is how I want to show you that H1 transpose. So this is how the output will look like. And you, if you do all this multiplication, you will get
Sir, why
this.
H1 transpose?
Okay, I just now went through it. A lot of discussion I
It
did, but
becomes a
to
scalar quantity
do I
tensor.
do I give you a resource? This is the reason why we have to do. So if you do this
Oh,
derivation, you'll get here similar thing always, and
uh,
you want to do this multiplication, so you will write this as a transpose of it, and you'll do outer product.
okay, sir. Okay.
Here it is. So that's how you can do. Now similarly, you have to do with the last W1, which is the uh, which has the most number of this derivations, right? But the good part is we have done till here, right? A2 till that we have done, like
Yeah,
A2, right? So
substitute in the
so this
chain.
part will not change, Okay, yes, what you have to compute and you have to figure it out. Now what will you do? So I'll call this the whole thing. I'll call it del L by del A2. Fine. Yeah, this part. Okay, so I have to do with respect to W1. So del L by A2 is what I'm calling this whole thing. Whatever just now, this except this row one, everything is in A2. So few things you have to do, three steps, which we have done here also. 1, 2, 3 calculation, this 3, and if you do it again, you will see that one thing will come out as W. So here it was W3, W2 transpose. Okay, and here it will come out H1, 1 minus H1, and here it will be X transpose. Okay, so again, it's a similar kind of things you will get. Uh, this is going to be a matrix. This will, if you do, it will be this will be a vector, column vector. This column, and this is row. Okay, nothing has changed from the above. This one part will be there, which you have already computed somehow uh, in previous computation. Okay, so this is how you can figure it out how to do the last weight also. So this is that. Now see each of this component. So here three things are there always in a backprop. One is you will do differentiation with the last layer H3 or A3 or something like that, which will always come out this. Now hidden units you will do, and that is also explained here. So if you this is with respect to weight. So here it is done as hidden units, right? So uh, yeah, backprop with respect to hidden unit, and you'll get this answer. If you do with respect to weights or parameters, then you'll get another kind of output. Uh, this one. Okay, so there's three kind of differentiation you'll do always, and you just have to chain it how you want to write. Okay. Now nothing is going to change. Most of the structure will be look like this only. If you do for more and more layers, you will see that the output is not going to change. Like so, this as on A2, some kind of loss with respect to A will be there, and then rest all are same. Fine.
Sir, here
Yes.
H1 is a vector. It contains negative values also, only positive values.
uh, Only does it contain negative values.
Why, sir?
So yes, right. So
0
sigmoid
to
looks
1.
like this 0 to 1. Yeah, no, it won't contain any negative value. Sorry, it is y, right? So 0 to 1. It won't contain any negative value.
H matrices. This H1.
Yeah, h1 any h. It's a sigmoid function, so it won't contain any negative value.
Okay, sir. Thank you, sir.
Okay, so that's all I have to explain about backprop. Now I guess you can do any of this. It's relatively easier now. Anything else?
Excuse me, sir. Can I ask you a question?
Yeah.
Sir, this is just a clarification regarding that graded assignment question. There one question they are asking about the summing of elements in H2, A1, A3, etc. And when what does that actually, whether it is to just to know whether it, our what we found is correct or not, or is it has any other relevance? The summing of elements.
Yes, only it's related to the uh, like you have found the correct answer or not. It has nothing to do with uh, any method of backprop or anything.
Okay, so we can calculate the loss as described in the this one that feed forward thing and fine. But how these sums come into the picture? That is why I asked.
Now, summing is something for the so that you have computed the correct answer. Like the question is numerical answer type, right? Or let's say MCQ also. Then you can choose only one answer. So that's why it is they've used summation as a way to figure out that the output is correct, your calculation are correct. It has nothing to do with the algorithm, right? So we have done this like that, let's say like here, right? So 0.91, 0.9, 2.49. If I sum this up and give you as output, sum this up and that's the answer of the question. But it has nothing to do with the any of the calculation of related to algorithm. Related to algorithm, no relevance. It has relevance with related to your answer is correct or not. That's all.
Whether we are having any mistake in the steps, that's what you mean.
Yes. So let's say you got answer as 0.8, 0.9 and maybe 2, something like that.
Right.
So this is an incorrect answer. If you sum it up, it won't sum to the correct answer. But correct summation should be whatever is this, right? So just to evaluate, nothing more. Evaluation on.
Okay, sir. Okay, thank you, sir. Thank you. And for one more thing, that loss you are telling, actually, when we find the loss, it's only for the classified that whether it that one only we have to test the loss.
Yes, because it's a cross entropy loss, right? So cross entropy loss is summation of uh, so y true, okay, whatever y is, and let's say I will write, and ln y I hat, okay, and let's say you have k classes, so 1 2 3 4 like that, you have k classes, then you have to sum all of them, so 1 till like k, okay, I equal to 1 to k. This is what a cross entropy looks like. But what happens is here we have yi or y true is like 0 0 0 1, something like this, and yi hat will come out some numbers, okay, 0. Let's say 4, 0.3, 0.2, 0.1, something like this, okay. This is how it will come out. Now if you do this, you'll see that first one will be 0, another will be 0, third will be 0, and last will be ln 4, which is 0.1. Okay, so this is what it looks like. So to not do all this computation and then realize that this is the one is the correct answer, what we have done is okay, this should be negative also, negative of ln y true, like whatever the true class is. Okay, so let's say L is the true class hat of that. So that's how this category, sorry, this cross entropy reduces to this one part only.
Sir, what is the value of dou L by dou y hat?
So dou L by dou y hat, if you do, so L is this, right? Y hat is
Minus 1 by.
this, so this should be minus 1 by y hat L.
So when we use this formula, sir, when we use y hat minus y,
that is dou L by dou AL. AL is before that. So what happens is, you have this, you'll get another matrix kind of thing. If you, so you have to see y hat is
Vector.
soft max, right? Vector, but soft max. For example, you have, for example, let's say this is AL. Okay, AL looks like it has some value P, Q, and R. Okay, so if you apply softmax on that, you'll get e power P and then
e power P, e power Q, e power R.
summation of this, right? And
Yes,
similarly, you will get with respect to Q and summation e power R and this summation. Okay, this you will get. Now you have to do y hat with respect to dou A. Y hat is this one, this whatever vector, and this is also vector. If you do this, you will get a matrix. Okay, and there's one portion which is so if you want to do dou A, so this is currently AL. There are two components, dou L by y hat with respect to AL. So this is a matrix. This is some kind of you'll see a vector. Okay. So this is a vector matrix. If you do a multiplication of this, you'll end up having one vector. Okay, and that vector is y hat minus 5. You can do this calculation to do this y hat with respect to AL. You will require one quotient rule of differentiation. So quotient rule is let's say you have two values u and v, and u by v. Okay, both of them are let's say function of some value. Okay, and you want to figure out the differentiation of this, you have to do u v dash
vu dash
and v square
divided by v square.
Something like this. Okay, if I'm mistaken, it's the other way around. You can check.
Sir, I think it should be v u dash.
I think it is u dash v and v dash, or no, wait, it should be u v dash and u dash v. Okay, something, yes, most likely this. If it is something different, so it is called quotient rule of differentiation. You can check it out. This is what it is. If you do this, you will be able to compute with respect to AL, and you will get a matrix. So this part you can do, and finally that matrix will get multiplied with a vector, and that vector will make it as a, so the multiplication will lead to another vector. So output will be vector, and that vector output looks like this. You can do this. Already just do this. Yes.
Sir, it is. I checked on the web, so it is v u dash.
Okay, so it should be u dash v and u v dash. Okay.
Yes, sir.
So this is quotient rule. You can do this. So here u will become like, for example, e power p, and the summation is what you can call as v. Okay, and you have to do this. So this e power p, and the summation was like, okay, e power p, e power q. So this is what it looks like. You can call e power p as u, and you can call this as v. So you have to do u dash. So if let's say you are doing with respect to p only, then it will be u dash will look like e power p. V is something I'll just call it as v only, minus, so u as it is. Now this you can do, you will get e power p only as output, and v square, right? This if you do, you'll get e power p by v 1 minus e power p by v. It will come down to this. Okay, so this is like y1 y1 1 minus y1 hat, I guess y1 hat. Okay, yeah, y1 hat. So one element. Okay, this is one element, and it will come down, boils down to this. If you do let's with respect to now q, and now again it is like e power p by e power p plus e power r. Again, if you do, then you can see this u dash will become 0 minus e power p, and here you will get e power q, and here you will get v square. Okay, so this you can write like minus y1 hat and y2 hat. So something, so this way you will get the whole matrix. This 3 cross 3 matrix you'll get, right? So as of now we have figured out two things. This was, and you'll figure it out. If you do that, you'll get this. Okay, and similarly you will get here y2 1 minus y2, you get y3 1 minus
y3
y3.
1 minus y3.
Okay. And others you can fill, like rest
Minus, no, minus.
it will be negative and something like of this form, like y1 y2. Yeah, it is going to be symmetric matrix. This is
Minus y3
y2 y3, something like this. So and then you will do a multiplication with y1 by y2 minus 1 by y3. Okay, so you can do this multiplication, and it will go away. This will go, yeah, this will go away, something like, I don't know, I made a mistake, but the final output will be y1 hat minus, sorry, y minus y hat, y hat minus y, yeah, something. Yes. Now somewhere I might have made mistake, but you can do it the rest. Okay, so this is a no, this is y hat with respect to a l, and then here this is now l by y hat. This is two parts. Yeah, this is related to soft parts, this differentiation. Okay.
with respect to h1, right? Differentiation with respect to h1.
H1, no.
H matrix, HL.
Uh,
This matrix represents.
no, this we did with respect to AL. This whole thing.
Not whole thing, sir. This one only.
With respect to AL.
Oh, okay, sir.
L with respect to AL. There is no H. We haven't reached H yet. That will come after this. Okay.
Sir, if the curve consists of both global minima and local minima, gradient descent will converge to local minimum only, right?
It's not
The one which is near.
that. Yeah, it's like it tries to do.
Which
See,
was near. Global
for
minima is near.
example,
Yes.
this is like a loss function. It will look like any kind of surface. Okay, we don't know. Uh, what we can do is we just have few points, few data points where we can plot the loss function. So for that we can plot it, and maybe let's say it looks like this. Now let's say if you start from here, you might end up here. Depends on where you
Local minima.
start the, yeah, how it starts the initial point, right? So it depends on initial point. Wherever you are, it will leads to the local minimum or any minimum which is most likely nearby.
Okay, sir.
And so sometimes, let's say if you use momentum gradient descent something, it might push off also. Let's say this is where it maybe shoots off, then maybe reaches here. Possibility, like we will never know if that was local or global or anything. We can't actually figure it out because we don't have this whole picture. We will never have this uh, actual picture of loss, and we can't see it also, right? So we just have few points where we can plot the loss for that.
And so can neural networks can they also be convex, or they are always non-convex in nature?
Which
So
one? Neural network.
so see, the convex or what, it depends on how you choose the loss function, right? So we always choose loss function which are not, which should not be uh, or which should be convex. It should leads to some minima, something like that. That's what we will always say. So that's why this category, so this cross entropy or something like that, it's they are they are kind of convex.
Sir, in MP neuron there is a property P union of negation of negative points n minus. If
Okay.
the decision boundary it classify the positive points and negative points. If the negation of negative points, what
Yes.
is that property, sir?
No, it's not property. It's a proof. So I think it's not related to MP neuron. Also, it's related to the uh,
Percept.
perceptron, right? And so perceptron. So let's say there are negative points and there are positive points. If this is a linearly separable, then you can draw a decision boundary. So how will you prove this? So this proving is something they are doing. That what they are doing is they are bringing negative also to positive by negating this. So if you do maybe negation of this, like, you'll get all of them as positive somewhere here, and then something they do. I don't recall the exact proof, but the negation is for that.
Is it like the way in SVM, in soft margin SVM, where negative were in the positive side also, and they were
No, no, it's, it's little easier than so. That is different. So the idea of SVM comes from this only, perceptron only. So after that soft margin all will come, but before that, this is very easy. Like we wanted to prove it that perceptron will always converge if it is linearly separable. So to do that, this is the proof of that. This is not property or anything. It's just proving it that yeah, it will work, right? Otherwise, how will I know that or what? Why should I believe that it will always converge, right? Maybe it will. This boundary will never converge and it will always fluctuate. So to prove that, this is a proof of that. You can read this proof that perceptron will always converge if it is a linear separable data. if linearly separable data is not there, then perceptron can't do much. But if it is there, then why it should always and always converge. To prove that this method was used, okay, we'll negate the negative points and then find the something. I don't recall exactly, but something like that. Okay. Then okay. If there are no further questions, we can close today's session.
Sir, can you repeat that last mapping part, sir? The negative points and positive points, what it was.
So okay, so let's say you wanted to prove the that perceptron will always converge, right? How will you do that? Think I have not here, but yeah. So this is in proof of convergence. They'll do this. So okay. So here, if you see what we are doing in the algorithm is we have positive points, right? Now what we are doing is we are calling negation of negative points as positive. Now we are doing that. So we just have to look for one side only. Like if uh, pick random p, something like that. If the summation will be less than 0, then do the change, right? So this change is this, make some changes. But if it's not there, then we don't have to do it. So when the algorithm converges, when all the inputs are classified correctly, so that's what it is, right? So now since all the points are in one side, it will converge if all of them are greater than this line.
Yeah, correct. Yeah.
So that's what it is. So that's proof. To prove it, we need to do this. That's all. Like, see,
Oh,
we can prove it other way also. Like we can use both and do it, but this is little bit simpler. Like it is kind of
okay, sir.
solid proof that
Mm.
it will work only. Okay. So to do this, we use some induction and all. Then they are figured out the angle between it, but and like that, right? So this is the algorithm. This is just to uh, see that how it is working and all.
Yes. Other way means what is that other way you told?
Other way means you take negative as negative and positive as positive. So that way you have to do two kind of updation, right? If it is less than 0 and if it is positive, then make a change. And another change is if it is greater than 0 and if it's negative point, then make a
Okay.
change, right? So that
If it lies
changes.
that side of the line, it will be.
Yeah. So both side you have to. So here, right? Like this was algorithm proof. Sorry, this was algorithm. It was working, and it has this is the right. But to prove it that it will always work, we need to do this. That's all.
Okay. Okay.
This proposition was given that if sets of P and E are infinite linear separable, the perceptron linear updates a finite number of times. In other words, if the vector P and N are tested cyclically one after the other, a weight vector W is found after a finite number of steps T, which can separate the two sets. That was the proposition, and to prove it, we are doing this. Okay. Uh, Yes.
Sir, and the angle between weight vector and the positive points is always less than 90 degrees. Always.
That's what the algorithm is. Yes. It has to be.
If the weight vector on the negative side,
No, it doesn't work that way. You you can't plot like that.
okay. How this cos phi value affects the loss value, sir? Cos phi here, cos beta.
So
If
cos
beta
beta
between
was
0 to 90 degrees.
uh, yeah. So no, this cos beta has nothing to do with the no, it has, but why cos beta was introduced, that we will require finite number of steps in which the algorithm will converge, right? So how will you know that the finite number of steps does exist? So since the cos beta, which is angle between the weight and uh, the real w, okay, so whatever is, so that should be there, right? So to make it, we will need, so see, by some x, some k will be there, and some observation you will see that after finite step it will converge always. To prove it, we require this. It has nothing to do with algorithm. So see, there are two things in this. One is algorithm, another is proof that it is working. So this algorithm is there, which is this one. Proof is that this will always work is here. So there are two different things. Okay, you in MLT you have learned algorithm. uh, Maybe proof is also there, but in different way. Here they are showing a proof a visual way. It's in a visual form, like some angle you are taking and all. Okay.
Yes, sir. Thank you, sir.
Okay. Okay then. I'll close the session now. Okay, thank you everyone.
Thank you, sir.
Thank you, sir. Thank you so much.